Now let's find the energy levels for the infinite well system. And again, remember, we already know the result, so this is just a check. So since U of X, the potential energy is 0 inside of the well, the energy is just equal to the kinetic energy, which is P squared over 2m inside the well, okay? And since P is just H over lambda, which is the same as H bar times K, that means that the energies are given by H bar squared K squared over 2m. And then finally, recognizing that K is quantized, so K is equal to n pi over L, we have H bar squared pi squared over 2m L squared times n squared, okay? And finally, if we like, we can cancel out the pi squared factor with the 1 over 2 pi squared inside of the H bars and rewrite this as H squared over 8m L squared n squared, as we did before the first time we wrote this down. Okay? So we get the same result that we got before. Okay? Perfect. So now we've found the allowed states and the allowed energies for the particle in an infinite well. And you can see it wasn't too hard and it's not too complicated. That makes this problem a really great test problem for anything else we might want to do. Here, let's do an example. Let's use what we've learned to normalize the wave function, okay? So far, we've written the wave function as psi of x is equal to a times sine of n pi x over L, okay? But what's a here? We can find a value for a by insisting that the wave function has to be normalized, that the probability of finding the particle somewhere within the box has to be 1, since we know that the particle cannot be outside the box. So what we're going to insist is that the integral of the probability density over all possible values of x be 1. Now, since the particle is known to be within the box, this is clearly the same as the integral from 0 to L of the probability density, since we know the probability density is 0 outside of the well. And then remember, probability density is absolute value squared of the wave function. And so this is a squared integral 0 to L sine squared n pi x over L dx. And this has to be equal to 1. And if we carry out the integral now, we can find an expression for a. And that's what we'll do next. Okay, and the rest of this is straightforward. Let's do a substitution. We'll let theta equal n pi x over L, okay? And then d theta will be n pi dx over L. And now we can make our substitution. Now, following this, we have a factor of dx, but dx is clearly d theta divided by n pi over L. And so we have a constant factor of L over n pi that we can bring out. Finally, let's look at the limits of the integral. When x is equal to 0, theta is equal to 0. But when x is equal to pi, when x is equal to L, theta is equal to n pi. Okay? And there we have it. And the rest of this integral is straightforward as well. Here, let's just go through it for practice here. So note that sine squared theta can be written as 1/2 of 1 minus cosine theta. Cosine 2 theta. Let's make that substitution. So we have integral from 0 to n pi of sine squared theta d theta can be written as 1/2 times the integral of d theta from 0 n pi minus the integral of cosine 2 theta from 0 to n pi. Okay? And this gives us two terms. So we have 1/2 of, well, the integral of d theta is just theta, so this just gives us n pi minus 0. And then the second term, the integral of cosine, is sine, so we have minus 1/2 sine of 2 theta evaluated at n pi and 0. Notice that when theta is 0, that we have sine of 0, which is 0. And when theta is n pi, we have sine of 2n pi, where n is an integer, also 0. So this second term just drops out. So the result of the integral is just n pi over 2. Continuing then, we're saying that 1 is equal to a squared times L over n pi times the integral, which evaluated to n pi over 2. The factors of n pi cancel out. That's good. And we have a squared L over 2. Or in other words, a squared is equal to 2 over L. So a is equal to the square root of 2 over L. And finally, we can rewrite the wave function now. The normalized wave function, psi of x, is equal to square root of 2 over L times sine of n pi x over L. Whew. Okay, that was a little bit of work. It wasn't so bad, but now we have a normalized wave function, and we can use that for other purposes now. In particular, we're going to use it for the next example. All right? Here, let's stop here and we'll start the next video about that.